buddy. Yeah, very cool, very cool. So I'm going to kind of tell you a little bit about my project, and then if you guys have any questions about really anything, I'll try to answer in the short amount of time that I do have. What I'm doing for my senior project is an adaptive filter. So I'm going to kind of start at the beginning and talk about what a filter is in general. So are you guys science semester students? Try to gauge where you're at as far as, you guys started talking about filters, analog filters, or anything like that?
Yeah.
And so you've got some kind of frequency waveform, maybe a sine wave, and it's a low pass filter. If that frequency gets too high, too many cycles per second, it's just going to wipe it out and attenuate it so that there's nothing output from this filter. What I'm going to do is an adaptive filter, which is similar. Obviously, it's going to filter, but it's going to change parameters based on two inputs. And a common example that you're probably familiar with would be like noise canceling headphones, which I kind of have a little diagram of. But you've got two inputs. You've got a primary input or sound or something you're going to try. With the headphones, it's going to be either the internal sound that you're trying to achieve. And somewhere else you're going to have a microphone, typically like on the outside of the headphones, that's going to detect some kind of noise. And it's going to compare these signals, obviously the one that's finally output, and that second noise, and compare the difference between them or the actual noise that exists afterwards. And we're going to adjust the filter, which is basically what I'm going to do. Although I'm not going to design noise canceling headphones, I'm actually just going to cut out a moving sinusoid. So I'm going to have a sine wave that's going to change in frequency, so it's going to kind of compress or expand. And as that changes, my filter is going to change, kind of seek it out and cut it out entirely. Any questions about that? You guys can interrupt me. And I'm going to do this on an FPGA. I don't know if you guys have played around with one of those or anything yet. What are you guys doing on the FPGA? You guys kind of draw your schematics right now when you start out, right? Yeah. The FPGA is a much, much more powerful tool than that. I mean, obviously you can make little digital circuits, but the beauty of the FPGA is that you can expand that and make very, very large digital circuits that you don't need to kind of pull every little piece into, your multiplexers and your adders or whatever. You can actually use a hardware design language, which is what I'm going to do, and what you'll do as you advance too. And you can actually tell it what you expect the outcome to be. So you might have a signal, and you might say, well, the signal output here is going to be this signal, plus whatever, and then it will kind of, it actually has what are called lookup tables that will say, okay, this is going to be an added signal, and it will just kind of do that for you. It's very efficient, a little tricky to learn the intricacies of the language. And so, basically I'm going to build a very large-scale digital circuit that's going to look at two signals and compare them to one another, and it's going to try to cancel that signal out. And as that signal moves, it's obviously going to grow because the filter's not designed to cut out that frequency. And so if that frequency increases, what's going to happen is it's going to kind of seek that out and kill it off there again. Involved with that is a lot of mathematics, and then it's those mathematics then translated into a digital system, which is for some people fun and others very tedious and complex. I don't, this is a very beginning stage. Next semester I graduate next May, and so next semester the majority of my time will be working on this, and I have some small programs to start from, but I've not done anything this large scale, and so that's kind of my project. Does anybody have any questions about that, or the senior project, or the 4-year program in general? Do I fill 10 up?
Yeah, basically, yeah. Like I said, I'll keep recording if some of these guys might have to leave for their 11 o'clocks, but most of these guys I think can stay a little bit longer.
How does the board know that the noise signal coming in?
How does it know the noise signal? Well, the signals are actually going to be together. In this instance, and it's going to have a general idea of where that noise is going to come from. An example of that might be, 60 hertz that it's picking up, inside of a system. And so I think that's what I'm going to do. I'm not 100% sure yet. But, that 60 hertz is stationary, but it can drift. Not very much, but just as an example. And so I might know that sinusoidal noise is going to range between 55 and 65 hertz. And then my other signal will probably be, some kind of music signal maybe. Right. And I'm going to splice the two. And so it's kind of going to know the noise. Again, it's just going to be a sinusoid, so it's going to be easier to make an algorithm or mathematical computations to detect that, as opposed to, the noise canceling headphone idea. Other examples of adaptive filtering exist, especially like in medicine. When you think of like a pregnant mother, and you're trying to do an ECG or an EEG. An EKG, thank you. Yeah, on the heartbeat, there are two heartbeats. And so how do you know which is which? Well, you put, microphones on both, right, and they both pick up both sounds, but from that difference you can kind of cut that out, as well as all the other noises that go on inside of it.
Yeah.
This is not going to be that complex, because it is a very complicated algorithm, especially to build on a digital. I mean, obviously these things exist, but you've got a lot of designers working on it.
Right.
How's it graded? How's it graded? That's a very, very good question. This whole semester, I'm taking a course that's called the Senior Seminar, and that's actually what I'm doing right here. I'm working on the Senior Seminar, and this is a freshman presentation that I have to do. And there are assignments to each week that you kind of work through how you're going to accomplish this project, what a completed project will look like, what are you going to do, oh crap, if all of a sudden this isn't going to work, what's your kind of risk assessment, your plan. It's based on using the tools that you learn in this program and, building something kind of beyond the projects that you do in class. So it's kind of vague, right? Yes, I mean, it's a course. It's a course. It's a 3-credit course called Senior Project or Senior.
Yeah, and there's 4 or 5 faculty that will grade the whole project, including the presentation. There'll be a rubric, et cetera, and an A, B, C, D, F is granted for that senior project grade. So that's basically how it works.
When do we start learning circuits that have to do with like real world applications? Like right now we're learning like AND gates and stuff. It's just, and they say they're not even used anymore because most of them are TTL. So
Yeah. The FPGA is very applicable. In fact, I'm looking to go into graduate school. Okay. And so, one of the things I was kind of going to talk about is that in this class, you guys made a resume. When I took it, you were gone, so we might have done some different things. But we didn't make a resume for this course when I was in it.
Yeah, we still do that, yeah. Mm-hmm.
And I kind of want to talk about my resume and how I, got the attention of some graduate instructors. And one of those things was that on my resume, I put the projects that I've done through my time here, and he was impressed with, especially the work I've done on the FPGA, which is those digital logic.
Yeah.
But you don't really look at it that way. I mean, it's very good to understand the inner workings because you're dealing with digital signals. You're dealing with on-off signals, but they're in a very large scale. I mean, on the FPGA, I can say, okay, I want a bus, that has 30 lines. So, or it could be a 30-bit number,
right?
And that kind of thing. And it's very quick and easy to type that up and implement it on a board. And so, that might be a more real sort of example. I mean, these filters that we're building are very real.
Oh yeah, definitely.
And that's not to say that the digital logic gates aren't. For the one course, not last semester, but the semester before, I used chips. I built it was analog also, but I had a digital display on it, and it was actually, it output a frequency or a pulse, like a pulse train.
Okay.
And the frequency or the
And that's why we switch over to this Digilent and Xilinx system so early in the semester now. This is what all you guys are doing now, right?
Yeah.
And so this is real world. Like in modern automobiles now and stuff, you're not going to see discrete dual underline package chips. You're going to see programmable logic. So by converting to this early, like we do now, we're actually getting you exposure to the way things really are done. And you could, yes, even though we're just doing multiplexers and counters implemented in here, it does give you the background to do more complicated things like Joe is talking about, all these signal processing. Because as you know, this CPLD device that you're programming, or is it FPGA? Which one? It's FPGA actually here. I mean, there's hundreds of thousands on there. It's just incredible what you could actually make with that thing. So.
No, this is a smaller. I mean, this is kind of like your bare minimum FPGA. I mean, some of them from the same company are designed with HDMI outputs, so you can really build some interesting.
Is this the one you're using, or are you using it?
No, I'm actually going to use the next step up, which is a Nexus board,
Okay.
which is I think it has a faster processor, not processor, but oscillator on it, so it can run a little bit faster. But it's also got a lot more logic gates, availability to it right on the table.
But you still use Xilinx, right? It's the same.
It's still the same software package.
Now, using VHDL, that's the language you're talking about?
Correct.
Yeah. And these guys, I think the last lab you used some VHDL, right? If I'm not mistaken. You implement like a simple counter. I don't know. We used to do it. You actually implement like a 4-bit counter using the VHDL statements versus drawing a schematic. So you kind of get a taste of what we're talking about. But Joe wouldn't take the time to build his, adaptive filter using the schematic entry. That'd be crazy, right? It'd take, yeah.
I don't even
So instead, he describes his system with VHDL.
okay.
And so in a few lines of code, that represents, maybe hundreds of logic circuits.
So you're basically programming it instead of actually drawing the schematic and making it recognize from that.
That's right. That's right. But it's different than programming like a microcontroller.
Right.
Because a microcontroller will take a line of code, and it'll do that line of code, and then it'll go into the next line of code, and the next, and the next thing. The FPGA doesn't do that. It's all parallel.
Okay.
It all happens
At the same
kind
time.
of at once, which makes it just, exponentially faster.
Okay.
One of the things that's required to do the filtering is you've got to have an A to D converter, which is going to take that analog signal, and it's going to sample it. So every so often, it's going to grab, whatever that is, and convert that to a discrete or, bit kind of sense value, a digital value. And so it's going to do that every so often, and so I'm going to have all these values in there. And I'm going to perform all these operations on, however many samples. And then it's going to spit that out with the D to A, converter. Well, the code, in order to do that, is very interesting because it has to send a bit to say, okay, ready, and then it's timed, so you've also got a clock there, that on each clock you're going to, grab these values. This chip, this A to D converter, is going to spit out maybe 12 bits for you, and they're going to be serial. So you got to know when to say, okay, I'm going to grab this bit, and then high or low, and put that into a register. Right, so there's a bunch of stuff going on. I mean, in order to, all the registers and memory, the board I even have memory, the next step. Yeah, I mean, it's kind of complex. Oh, yeah. Any other questions about anything really going on?
Yeah. And you'll see Joe around a lot, so if you see him and you have questions, just...
If you guys have any questions about anything
Yeah.
before I'm going, like I said, I'm looking at going to graduate school to study electronic engineering. Hopefully, I can impress the professor down there enough that he wants me to come work for him. But he's actually doing speech recognition, kind of work right now.
What school is this? Is this
Bucknell.
Bucknell? Oh, awesome. Yeah.
And he wants to try to implement some of his algorithms on the FPGA, which he's not especially familiar with. So we might be a good match there. But the speech recognition is similar. I mean, you're taking signals from the outside world that can pertain to anything. Any kind of information that you would detect, can be broken down into a signal, and we're going to, process them, digitally, so that we can. It allows for easier manipulation.
Yeah, great. All right. Any other questions or? Okay, let's give Joe a hand for his presentation. All right, awesome. All right. Thank you, Joe.